Okay, so this is the my screencast solutions for the homework. Some of these I've actually done as a screencast to help you. So, for example, this one, PC10C, I did for you. This one, I guess it was PC29D, I did for you. And this one, PC30, I did for you. So I'm not going to talk about those here. You can still look at the answers here, though. So going back up, for this one, again, for these, you're looking mathematically at the formula for Ohm's law, which is current is equal to potential difference divided by resistance, or you could think of it as potential difference, which is voltage, is equal to current times resistance. You could also rearrange this as I've shown down here. Resistance is the same thing as potential difference over current. So in this case, then it's asking about the resistance of a power saw when plugged in. I don't know why I initially gave the wrong units here. Maybe I'll see if I can knock that out. Get this here, no border. See if I can do the fill as a slight. No. And I'll just keep that out. Never mind. Okay, so 7.33 ohms. Here, you need to recognize that 3 milliamps is 3/1000th of an amp. Again, hopefully you can do conversions at this point of the year. You've got 1200 volts as a taser, and essentially if that actually is applying or causing 3/1000th of an amp through the body, you can use Ohm's law to figure out the resistance of a human body, which is about 400,000 ohms. In reality, it ranges from somewhere between, say, 50,000 to close to 1,000,000 ohms, depending on things like your skin thickness, whether you have any breaks in the skin, whether you're sweating, stuff like that. Okay. For PC10, A, B, C, and D, and again, I did C as an example, so I'm not going to do that again here. That was my previous video. What you want to recognize is that power, which is in watts, is the same thing as joules per second. It's a rate at which energy is converted from electric potential energy to something like heat or light. So we've got 1500 watts, which is 1500 joules per second. I multiply it by 5 minutes. I guess I could do that over 1. And multiply that by 60 seconds per for every 1 minute, and this gets 450,000 joules. I don't know why I was going to put a comma there, but I obviously used whiteout on that. This one, same idea. It's for 4 hours, so 950 joules per second times 4 hours over 1, 60 minutes per hour, 60 seconds per minute. You could do this in one fell swoop as 3,600 seconds per hour if you know that conversion. So this comes out to about 13,700,000 joules. Same thing here, 2.27 million joules as our answer. For 18, I should have left a little bit more space here. So high voltage power lines of around 400,000 volts deliver electrical energy at a rate of 1,500 megawatts, or 1.5 billion watts, or 1.5 billion joules per second. So if you know your power formula, P equals V times I, we can rearrange that, I equals P over V, to get our current, which is about 3,750 amps. And then you can use Ohm's law, which I wrote over here, rearranged over here, to figure out that it's about 107 ohms. So not 1,070 ohms, that is supposed to say 107 ohms. Looks like 1,070, sort of. So anyhow, for number 20, find resistance of these two 6 and 8 ohm resistors in series. You just add them up. That's 14 ohms. To do this in parallel, you add the reciprocals, and then you've got to take the reciprocal of that answer, so the reciprocal of this, because 1/6 plus 1/8, which is basically 0.1667 plus 0.125 equals 0.292. 1 over that is equal to 3.43 ohms. And again, on the practice that I did for you, I'm showing you how to do that on a calculator. Note that the x to the -1 button or 1 over x button both mean reciprocal. So for this one, for 21, and again, I don't know why I wrote the wrong answer here initially, but I had 18, it's actually 20, which we just did. What we're doing here now is figuring out the current in the circuit if there's a 12-volt power source. So 12 volts divided by 14 ohms, 12 volts divided by 3.43 ohms, 0.857 amps, 3.50 amps here. So I assigned both those problems so you didn't need to figure out the resistance again. 25 is asking you to figure out the ammeter readings and voltmeter readings. So there's 1, 2, 3, 4 ammeters, but hopefully you remember that current in a series circuit is the same everywhere. So we do not need to figure that out 4 different times. First thing I always do when solving for a circuit is find the total resistance. In a series circuit, I just add up the resistors. That's 38.3 ohms. To get the total current, you take the total voltage divided by the total resistance. That gives me 1.57 amps. So that's the same for all the ammeters. Finally, to find the voltage reading across each resistor, we're going to use Ohm's law and rearrange that. So that's potential difference, or delta V equals I times R1, I times R2, I times R3. Current's the same everywhere. This comes out to about 16.2 volts, 23.8, and 20.1 volts. As with all this, the answers in this worksheet, depending on how you round here, like this was really 1.566, I think, amps, your answers could be a little different. These are figuring out all sorts of resistances when doing parallel resistors. So it's basically just getting really good at doing that reciprocal type thing that we initially did up here. So I'll just let you take a look at that for a minute. One thing to notice here, 8 ohm and 8 ohm, 4 ohms is the equivalent. So it's basically half of the total. 2.5 ohms is the equivalent. It's half of each, not half of the total, but half of each individual one if they're the same. Same way here, half of each individual one if they're the same. Now for C, D, E, and F, you've got a 5 ohm resistor in parallel with other resistors which are continually increasing from 8 to 9.2 to 27.1 to 450. Your resistance does increase as the second branch resistance increase. So it goes from 3.08 to 3.24 to 4.22 to 4.95. But notice, even when this second path gets a very high resistance, meaning very little current goes through it, the total resistance is still less than 5 ohms. You'll never be able to get more than 5 ohms because even if the second branch had 1 billion ohms of resistance, a tiny little bit of current gets through. That means the total current in the circuit would be the same as through this path plus a tiny little bit extra, which means our resistance would just be a tiny little bit less than 5 ohms. So anytime you have more paths in a parallel circuit, you have less resistance. For number 30, I did this on my earlier video, so I'm not going to talk about it here. I will show the answers again. These double slashes are just to separate parts B and C. For PC 32, what I've got here is a parallel circuit. I've got 1, 2, 3, 4 ammeters, which I've labeled A total, A1, A2, A3. I don't know why that 1 is so small. And 3 voltmeters, V1, V2, V3. So first I'm going to get the total resistance again, doing the reciprocals. That gets me a total resistance of 14.16 ohms. Probably could have rounded that, but a lot of these answers are like 0.16 or something, which, you know, kind of annoying. You're off by a bit more than you'd like. It was 0.19 or 0.20 or something like that. So anyhow, second thing is I'd find the voltages, but since these are in parallel and these are across the resistors, then each of them would have the full voltage of 24 volts. So to find the current ammeter readings for the total current, which is right here, notice that's after the current splits into 1, 2, and 3 paths. The current has all come back together by this point, and that's why it's the total current. So I take the total voltage divided by the total resistance, that gets me the total current. And then finally, when I end up doing this, the current for each branch, A1, A2, and A3, is simply the 24 volts divided by the resistance of that branch. And these three should add up within a reasonable amount of rounding to the total current, which is 1.69 amps. So hopefully that makes sense.